I want to take a look at a few problems that are similar to some problems you might end up seeing on the Chapter 8 test. So in this first problem, in the first couple problems, we're finding the geometric mean between a couple numbers. The way we're going to set up a geometric mean question is we're going to start with a blank proportion, two fractions that equal each other, and we're going to take the two numbers that we have to find the geometric mean for, and we're going to fit them into these two spots diagonally across from each other. Then we're going to put x's, or whatever variable you want to use, in the other two spots. And then we cross multiply to get x squared equals 8 times 18, which is 144. So now x would equal the square root of 144. And since the square root of 144 comes out as a nice whole number, we'll just write our answer as x equals 12. But in problem B, we're going to set it up the same with 9 and 40 diagonally across from each other, and x is in these two spots. What's going to happen here is we'll have x squared equals 9 times 40, which is 360. And x is the square root of 360. But that does not come out as a whole number like it did over here in part A. So what we're going to do is we're going to take the 360 and we're going to break it up into a perfect square times something else. And we're going to look for the largest perfect square that we can divide 360 by, which is 36. And so we turn 360 into 36 times 10. Now the square root of 36, it's going to come outside the square root as a 6. And this 10 stays underneath the square root as a 10. So x is equal to 6 square root 10. Now in this next problem, you can see we start with a large right triangle which has the altitude drawn from the right angle across to the hypotenuse. And this is the kind of problem where we have to remember that there are going to be three proportions that we can set up, each of which involve a geometric mean. The altitude will be the geometric mean between two parts, and then each leg will be the geometric mean between two parts in this picture. So if we start with x, the altitude, it's the geometric mean between the two parts of the hypotenuse, which would be 9 and y in this case. Now we can't do much with that because we have too many variables. We have two variables. If we move over to z, it's going to be the geometric mean between the part of the hypotenuse that's adjacent to that leg, which would be y, and the entire hypotenuse, which is y plus 9. Again, two variables, so we can't do much there. But if we come to this other leg, the 21, it is the geometric mean, again, between the part of the hypotenuse that's adjacent to that leg and then the entire leg. The entire hypotenuse. So now if we see here we only have one variable. So we're going to cross multiply this guy. We're going to do 9 times 9 plus y, which is 81 plus 9y. And that's going to equal 441, which is 21 times 21. So that means 9y equals 441 minus 81, and 441 minus 81 is going to give us 360. And that would mean that y would equal 360 divided by 9, which is 40. We actually found that right up there. Now we can go back and we can put this 40 in for these other two measurements for where we have a y. So this is going to be a 40 now, and that's going to be a 49 because 40 plus 9. This right here will be a 40. So now right here, oh look, it ends up being the exact same problem as I had up here. I actually didn't do that on purpose. X squared equals 360, so x equals 6 square root 10, which we already figured out right there. Here we have z squared equals 40 times 49. 40 times 49 is 1,960. Now 1,960 is 4 times 10 times 49. I actually just took the 40 that I used right here and broke it apart into 4 times 10. And that means that z would be equal to 2 times 7 times the square root of 10, which we will write as 14 root 10. So in these problems you need to remember what are the three parts that are the geometric means. That would be the altitude, and then each of the legs. And then remember, what are they the geometric mean between? The altitude is the geometric mean between the two parts of the hypotenuse. And then each leg is the geometric mean between the part of the hypotenuse adjacent to the leg and then the whole hypotenuse. So the 29 would be the geometric mean between 9 and then all of the hypotenuse. In the next problem, we have a right triangle. We have an isosceles right triangle because the two legs are adjacent to each other. Are congruent to each other. So we need to remember in a problem like this that this would end up being a 45, 45, 90 right triangle. And in a 45, 45, 90, the hypotenuse is equal to the leg times the square root of 2. So if I look at my two variables in this picture, first of all, I already know that x right here, x would be 45, because like we said, it's a 45, 45, 90, which means that the two acute angles are 45 degrees, and then we have the 90-degree angle there. To find y, we're going to take this hypotenuse equals leg root 2, and we're going to substitute in the values for the two variables that we have in the picture. For the hypotenuse, we have 12. For the leg, we have a y. So now 12 equals y times the square root of 2. If I divide both sides by the square root of 2, then I end up with y by itself and 12 over square root 2 on the other side. But now I have a square root on the bottom of a fraction. I can't have that, right? I need to rationalize that denominator by multiplying the top and the bottom by the square root 2. That's going to give me 12 root 2 over the square root of 2 times the square root of 2. Well, that turns into the square root of 4, and the square root of 4 is 2. Lastly, I notice that I can simplify this. I can divide the top and the bottom by 2. And so now I have 6 root 2 over 1, which is just 6 root 2. In problem 4 down here, what I have is a 30, 60, 90 right triangle. And in the 30, 60, 90s, I need to remember that the hypotenuse is 2 times the shorter of the two legs, and the long leg is the short leg times the square root of 3. So if I start with this one, I know that that is going to play the role of hypotenuse in these formulas. The B, well, it's across from the 30-degree angle, so it's going to be my short leg. And A will be my long leg because it's across from the 60. So now I can take these two formulas and I can set up equations using those formulas and using what the picture gives me. So 18 is equal to 2b, and a is equal to b times the square root of 3. So you can see I need to start here with this equation to find what b is so that I can sub that value in right here to find a. So if I divide both sides by 2, it tells me that b is equal to 9. So now I can cross that out and put a 9 there. And now a would equal 9 times the square root of 3. So those would be my two answers. In the next problem, you can see I have a right triangle, and I know two of the sides. A 2 root 5 for one of the legs, a 5 root 3 for the hypotenuse, and I'm looking for the other leg. Remember, when I know two sides of a right triangle, I can use the Pythagorean theorem, a squared plus b squared equals c squared, to find any missing side. What I need to remember is that the c right here always has to be the side across from the right angle. So I would set this up as a squared plus 2 square root 5 squared equals 5 square root 3 squared. And you're probably going to use your calculator to square these two amounts. And remember that when you put that in your calculator, you need to make sure you're telling your calculator to square all of this, not just the square root 5. If you do it correctly, it should end up like this. A squared plus 4 times 5, which is 20, equals 25 times 3, which is 75. And that would mean that a squared would equal 75 minus 20, which is 55. And that means that a is equal to the square root of 55. And since 55 is just 5 times 11, we can't actually simplify that. And we'll just leave our answer as the square root of 55. Now in the next problem, we get to use SOHCAHTOA. Remember SOHCAHTOA? It's spelled SOHCAHTOA. Stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. You need to remember this only works for right triangles because it has, the word hypotenuse used a couple times there. It should kind of remind you that you can only use this in right triangles. So in this picture, you can see that I know that this is a 71-degree angle. We have a right triangle, and one of the legs is 8, but I want to know the other two. So let's start by trying to find x. If I use this 71-degree angle, then I recognize that this would be the opposite leg, and this guy would be the adjacent leg. So if I'm going to use this 71-degree angle, then I want to set up a tangent ratio. I want to set up the tangent of 71 is equal to 8 over x, because I know opposite and I want to know adjacent, and that tells me to use tangent. So now, since my x is on the bottom of this fraction, I used the little trick we learned, which is to say that x equals 8 divided by tangent 71. And so that gives me a value of 8 divided by tangent 71 on my calculator. It gives me a value of about 2.8. About 2.8 for the value of x. Now to find y, I need to recognize that that is the hypotenuse. And so since I want to use the given information, just in case I got my x wrong, that means I want to use opposite to try and find hypotenuse. And that would say use sine. So I say the sine of 71 is equal to opposite over hypotenuse. And now y would equal 8 divided by sine 71. And that is going to give me a value of about, let me just double check here, about 8.5. And again, when my variable is on the bottom of this fraction, I flip-flop these two guys. If your variable is on the top, then you do a simple cross multiplying to get x by itself, or whatever your variable is, and you'd end up multiplying these two things when you do that. Let's take a look at number 7. In number 7, I need to find an angle measure and a missing side. So first thing, let's find the angle measure first. Let's realize that for this angle, I know something about it. I have one of its fingerprints, if you will, if I'm using kind of a metaphor that I used in class a lot. I know that for this angle, the adjacent leg and the hypotenuse make a ratio of 10 over 13. And that would be the cosine ratio for that x. The cosine of that x is 10 over 13. And since there's only one angle that has that particular cosine ratio, I can ask my calculator which one it is, what angle specifically has this cosine ratio. And I'll do it like this. I'll say x would be equal to whatever my calculator tells me is the cosine inverse of 10 over 13. That's my way of asking my calculator which angle fits in right here, which angle has this cosine ratio. So I do second cosine on your calculator of 10 over 13, and I end up with about 39.7. X would be about a 39.7 degree angle. Now to find y, I could use SOHCAHTOA again, but in doing so I would have to use this answer, which I'm maybe not sure is right. So I would try and find maybe a way that I could just use the given information. And I would notice that I have two sides of a right triangle. And so I can set up a squared plus b squared equals c squared, recognizing that the 13 is across from the right angle, so it's got to go right here. And I can say that 10 squared plus y squared equals 13 squared. So now that means y squared is equal to 13 squared minus 10 squared, which is 169 minus 100, so that'll be 69. And so y is the square root of 69, and that's not going to have, that's only divisible by 3. You can take 69 and divide it by 3 and make 23 times 3, but neither one of those is perfect squares, so we'll just leave it as the square root of 69, or we could maybe type it in our calculator if the instructions allow us to do that, and we can get about 8.3. Either one of these answers would be good. This is technically the better answer because it's more exact. This is an approximation, a rounded answer. All right, I think I have a couple more I want to take a look at. In this problem here, we have a little bit of a more complicated picture, and we're gonna use a couple different things that we learned in this chapter. We have to find these two side lengths, and what we know is that this is a 35-degree angle, this is a 30-degree angle, and this is 18 right here. Now I can't set up any kind of SOHCAHTOA ratio with the 30, the 18, and the y, because this triangle is not a right triangle, and so SOHCAHTOA doesn't apply. Some people will want to do that. They want to maybe say that they want to say cosine of 30 equals y over 18. But the problem there is this is not a right triangle. I can't use this 35-degree angle right off the bat because I only know one side of this triangle at the outset of this problem. So what I have to actually do is I have to kind of find it. There's an intermediary step, a kind of a middle step that I have to take, which is to recognize that this is a 30, 60, 90 right triangle, where the hypotenuse is 18. And that would tell me that this side here, which would be the short leg of this 30, 60, 90, this would have a length of 9. And what that means is now I can set up a SOHCAHTOA type situation for this little triangle right here. Now I'm looking for the opposite leg, and I now know the adjacent leg for the 35-degree angle. So that says set up tangent. Tangent of the 35 would be opposite over adjacent. And now with my variable on top, like I talked about a couple minutes ago, that variable will now just equal 9 times tangent 35. And 9 tangent 35 is about 6.3. So x is about 6.3. Now this whole side right here, that's the long leg of my 30, 60, 90 that I was talking about a few minutes ago. So that will equal the short leg times the square root of 3. And 9 times the square root of 3, if we're going to turn that into a decimal, is going to be about 15.6. About 15.6. So if this part of it is 6.3 and the whole thing is 15.6, then y will be equal to 15.6 minus 16.3, or sorry, not minus 16.3, minus 6.3. So 15.6 minus 6.3 gives me an answer of about 9.3. So those will be my two answers to that problem. Lastly, we have the application problem. It says a building casts a shadow 40 feet long when the sun's angle of elevation is 58 degrees. Find the height of the building. So we have a situation where we have a building and its shadow would be this distance right here. That shadow is 40 feet long when the sun is at an angle of 58 degrees. I didn't guess, that doesn't look nearly like a 58-degree angle, but you get the idea. And the question is, how tall is that building? Well, of course, we're measuring height perpendicular to the ground. So from the perspective of this 58-degree angle, we want to know the opposite leg when we know the adjacent. So we set up tangent of 58 equals h over 40, opposite over adjacent. And now h is on top, so it's simply equal to 40 times tangent 58. And 40 tangent 58 gives me an answer of about 64. So the height of the building is about 64 feet.